Hello everyone. Welcome to the next e-lecture. Myself, Professor Neha Sharma from Department of Computer Engineering, KK Institute of Engineering Education and Research, Nashik. We are NAC A accredited and NBA accredited for 8 branches. In this particular e-lecture series, we are covering one of the courses from PE Computer Engineering 2015 course syllabus, and the course that we are going to study belongs to semester 2, and the name of the course is Design and Analysis of Algorithms. In this particular e-lecture, we are going to cover one of the topic from unit number 3, and the topic is merge sort using divide and conquer. So let us start now. As per our usual practice, we will first start with the objectives and the outcomes of this particular e-lecture. So the objective of this lecture is to apply divide and conquer strategy to design merge sort algorithm. Outcome is, at the end of the lecture, we will be able to design the algorithm for merge sort using divide and conquer strategy. We will be able to analyze and comment on the complexity of the algorithm. We will also be able to sort a given input using the algorithm of merge sort, and we will be able to build the tree of calls of merge sort, and we will also be able to build the tree of calls of merge. So let us start now. Before we directly jump on to the algorithm of merge sort, let us quickly summarize about the general divide and conquer strategy. So this is a general design paradigm of any algorithm that follows a divide and conquer approach. The first step is to divide. Divide what? Divide the given input S into two subsets. Here, in this case, two disjoint subsets S1 and S2. Okay. The next step is recur. Recur means what we are going to do is we are going to solve each of the subproblems. That is, we are going to solve S1 and we are going to solve S2. Okay. Then once both the subproblems have been solved, now the final phase is of conquer. What we do in this phase is we combine the solution obtained from S1 with the solution obtained from S2, and we finally get the solution for the problem S. So this is a general divide and conquer approach that any algorithm, if we are solving using this particular approach, it will be by and large divided into these three steps: divide, recur, and conquer. Okay. So now we will start with the merge sort algorithm. In this case, whenever we are following divide and conquer approach, as it is, we know that we will solve any problem using divide and conquer, then we are going to use the concept of recursion. So whenever we are using recursion, our problem splits, and then we go on calling recursion again and again and again. So obviously we are going to reach a certain phase wherein the size of the sub problem is either 0 or 1. That will be our base case. Okay. So base case appears when you can no longer divide the problem into further sub problems. Okay. So whenever this base case reaches, that means you have to stop with the first phase, that is divide. Then you go to the next phase, solve the sub problems, and then finally you combine the solutions. Now here we will just quickly again summarize what is the general equation of recurrence for any divide and conquer algorithm. We have seen that T of n is represented by equation of time complexity, where n is the size of the problem. So if T of n represents the complexity of any particular problem, then T of n is equal to T of 1 when it is equal to T of 1 when size of the problem is 1. So when n is equal to 1, you need not solve it using divide and conquer because the problem is small enough. When this is not the case, that is when n is greater than 1, that means you need a split. You have to divide the problem into sub-problems. So in that case, T of n will be equal to A T of n by B plus f of n. Now we know that we have already seen what is A and B. A is nothing but total number of subproblems, and n by b is size of each subproblem. So if it is n by 2, you are dividing the problem into two equal halves. If it is n by 3, then you are dividing it into three halves, and so on and so forth. Okay, so that is A and B, and f of n is nothing but it is time required to divide and time required to combine the solution. So that is represented by this function f of n. Okay, and we regardless to say that n in this case, we all know that it is a power of k. Okay, so n is equal to b raised to k, right? So now we will see how we have to solve the problem using merge sort. So this is a general algorithm for merge sort. As we can see that it has two parameters, low and high. Low represents the pointer to the first element and high represents pointer to the last element. So we are solving a particular input. We want to sort a given input. So in this case, input will be an array of shuffled numbers. It is not sorted. We have to sort it using the algorithm of merge sort. So let us assume that our input is in an array, and the pointers low and high point to the first and the last element of that array. Okay. So as per our general divide and conquer control abstraction, we know that the first thing that we have to do is we have to check whether we have to apply divide and conquer or not. Okay. That is if the problem is small enough or not. So that is the first condition we are checking. If low is less than high means there is more than one element. Okay, only if there is more than one element, then you need to apply divide and conquer. If only a single element is there in the array, then there is no need of split. It is already sorted. Okay, so that is the reason why we are checking this. So if this condition is true, only then you have to go to the next step. Okay, so what we are doing now, we have to divide the problem into two halves. We have to split our problem P into two halves. Okay, so for splitting it into two halves, we calculate the mid. Okay, so mid is equal to low plus high divided by 2. So obviously our first half will be from low to mid and second half will be from mid plus 1 to high. Okay, so that is our next phase. So this, when we are splitting it into two halves, okay, that is our divide phase. Then we have to solve each of the subproblems in as per our recur phase. So what we are doing here is we are making again a recursive call to merge sort. First time with the parameter low and mid, that is with the first half, and second merge sort call is with the parameter mid plus 1 and high, that is with the second half. So here this will split the first half, this will split the second half. Okay, so that is our recur phase. We are trying to solve both the subproblems. Okay, now once we have solved the first problem also and second problem also, then we have to finally use the last phase, that is conquer the solution. For that purpose, we are using the algorithm merge. Okay, so we have to combine the solution. So merge has the parameter low, mid and high. Okay, so this is by and large the flow of merge sort algorithm. So we first check whether there is a need of split. If there is a need of split, then we calculate the mid. Once the mid is calculated, we call merge sort with the first half and we call merge sort with the second half. Once this is done, we finally combine the solution using the algorithm merge. Okay, so how this exactly works? For that, we have to understand the algorithm of merge. So we will see that now with the help of merge algorithm. So this is an algorithm for merging. Okay, as you can see, there are three parameters: low, mid, and high. Okay, so first we will initialize some of the pointers that we will require through our algorithm. First is H and I, we are initializing to low, and J, we are initializing to mid plus 1. That is, J is pointing to the first element of the second half. H and I are pointing to the first element of the first half. Okay. Now, we are applying a while loop. So what conditions we are checking here is we are checking two conditions. First is while h is less than equal to mid. Now what we are trying to check here is, we know that H is pointing where? To the first element of the first list. Okay. So we are checking here whether there are some elements in the first list. What will happen if H crosses mid? That means your first list is already over. Okay. Similarly, in the second condition, we are checking if J is less than equal to high. So initially J is pointing where? To mid plus 1, that is first element of the second list. Okay. So when J crosses high, that means your second list is covered. Okay. So that is the two pointers and the two conditions we are checking with those pointers. Okay. So initially our both the conditions will be true. So we move inside the loop. Okay. So as we know that H is pointing to the first element of first half and J is pointing to first element of the second half. Okay. So we compare the first element of both the list. Okay. So whichever element is smaller, that we will copy in an auxiliary array B. Okay. So if A of H is smaller, we copy A of H in B of I and increment the H pointer. If A of J is smaller, then we copy A of J in B of I and increment the J pointer. Okay. Whichever condition is true, at the end we have to also increment the pointer I, because that is the pointer with which you are using the auxiliary array B. Okay, so anyway you are copying in that array, so you have to also increment the pointer I. Okay, now this is about the while loop. When will we move outside the while loop? When either this condition is false or this condition is false, right? So we know that this condition is false means you have already covered all the elements of the first list. Second condition is false means J has crossed high. So you have covered all the elements of the second list. That is what it indicates. Okay. So that is exactly what we are doing in the next if else part. So here in the if part, we are checking whether H has crossed the mid. That means whether H is greater than mid. If this is so, that means only thing we have to do is we have to copy all the remaining elements from the second list. Okay, as it is. So that is what we are doing here. For k is equal to j to high, do copy all the elements, that is a of k into b of I and increment I, right? Okay. If the other condition is false, okay, then what we have to do is we have to simply copy all the elements from h to mid as it is into the array. So that is exactly what we are doing in the else part. So for k is equal to h to mid, we are copying all the elements into b of I as it is. Okay, and increment the I pointer. Finally, if we want our result in the array A, okay, so what we have to do is we have to simply copy all the elements from B of k to A of k, because B was an auxiliary array. So this is the extra space that we require for using this merge sort algorithm, which is required for merging. Okay, so then copy all elements from array B to array A. So our final result is now in the array A. Okay, so this is our algorithm for merge. So for better clarity, let us see how this algorithm, these two algorithms actually work with the help of example. Okay. Yes. So let us assume this is our array. Okay. So as we know, our first step is to divide. Since there are more than one element, we have to split. So we have to split at the exact middle location. Okay. So we must split it into two halves. This is our first half. This is our second half. Okay. Now what will happen? These four elements will go here in the first half. Next four will go in the second half. Again, there are more than one element. So we again split into two. Here also we split into two elements in each half. Okay. Again, there are more than one elements. We again split into individual one. Okay. So at this phase, our divide phase is complete. Okay. Now let us assume this is your first half. This is your second half. Okay. Now you use the algorithm for merge. Okay. So your h pointer will point to 8 and your j pointer will point to 2. So you simply compare a of h and a of j. Which is smaller? A of j is smaller. So you compare, so you copy a of j into the array. Okay. And then what is remaining is your, this list is over. So what you have to do is simply copy all the elements from the first half as it is. So 8 comes here. Okay. Similarly, here you compare 9 and 4. Whichever is smaller will come first. So 4 goes here, 9 goes here. Similarly, with the next half. Okay. Now, here, this is your first half. This is your second half. Okay. So you compare now 2 and 4 first. Which is smaller? 2 is smaller. So 2 will come here. H pointer will get incremented and will now point to 8. So you now compare 8 and 4. Which is smaller? 4. So 4 will come here and pointer, J pointer will increment and will now point to 9. Now you compare 8 and 9. Which is smaller? 8. So 8 will come here. Okay. Now when you increment the pointer, you have already covered all the elements of the first list. Okay. So all you have to do is you have to only copy the remaining elements from the second half. So you will copy this 9 as it is here and you get this list. Okay. Same thing applies with the second half. Now this is your first half. This is your second half. Again, when we apply the same process, same algorithm of merging, the final solution that we will get is this, which is a sorted list. So this is how our algorithm of merge sort actually works. Just to show you the use of an auxiliary array and how the sequence of merging operations happen, this is one slide. So let us assume this is your first half, which is sorted. This is your second half, which is sorted. So A of H is pointing here, A of J is pointing here. So you compare A of H and A of J, whichever is smaller. In this case, this is smaller. So you will copy this one here in the next step. Okay. And you will increment the J pointer, which now goes to 3. Okay. Now you will again compare 2 and 3, which is smaller. 2 is smaller. So you will copy 2 next here. Okay. And the pointer is now incremented to 4. Okay. Then you compare 4 and 3, which is smaller, 3. So you will then copy 3 and you will increment the pointer now to 5. Then you compare 4 and 5, which is smaller, 4 is smaller. So 4 will get copied here and the pointer will now increment to 8. Then you will compare 8 and 5, which is smaller, 5. So 5 will get copied here and then pointer points to 6. In this way, the process of merging takes place, and whatever is shown here in yellow, this is your array B. Okay. And this is your array A, which is your original array. So this is how the algorithm actually works. Now we will see whatever we have seen just now in the form of tree, how the sequence of calls will be. Let us assume you have to sort a list of 10 elements. So your we have seen that algorithm of merge sort has two parameters, low and high. Low points to the first element and high points to the last element. So let us assume 1 is our low, and if you have an array of 10 elements, your high is 10. So with the algorithm of merge sort, we split it into exact two halves. So then the next call of merge sort will be, first half will be with parameters 1 and 5. First 5 elements go in the first list. Remaining 5 elements go in the next list, that is from 6 to 10. Similarly, in this case, again, when you split, okay, first half will be from 1 to 3, second half will be from 4 to 5. That is, in this case, there will be 2 elements. In this case, there will be 3 elements. Similarly, in this case also, from 6 to 8 will be your first half. From 9 to 10 will be your second half. Okay. Just remember this, whatever is here, it is nothing but your pointers. Okay. Or you can say these are the indices of your array, not the actual elements. Okay. So just remember, this is simply indicates the index elements or indices to your array, given array, input array. Okay. So that is how the split happens with the merge sort algorithm. So finally, when you come here, when there are only 2 elements, it will then get sorted, it will then get splitted into one element each. Okay, so in the first half there will be a single element, in the second half again there will be a single element. Okay, so this is how the tree will get splitted, or rather your input will get splitted when you make calls to the recursive calls to the merge sort algorithm. Okay, similarly we are also using recursive calls to the algorithm merge. Okay, so for that we have to take this as a reference. Okay, so assuming that you have 10 elements, okay, and this is how you use the split of merge sort algorithm. So when you check this level, bottommost level, here you have first element, second element, and then third element. Okay, so taking this into reference, how will be the call of merge that we will see now. So this was first element, again mid will be 1 and 2 will be high. Okay, so this is your first call to merge algorithm. Okay, then you move one level up. Okay, so then the next call to merge will be with parameters 1, 2 and 3. Okay, similarly on the other side of the algorithm, that is this side. Okay, so this side what will happen is there will be a call with parameters 4, 4 and 5, and then when you take these two and you try to combine the solution, then your low will be 1, mid will be 3 and high will be 5. Similarly, similar kind of a thing happens with the second half, and then when you finally merge these two parts, your final call to merge will be with parameter 1 as low, 5 as mid, and 10 as high. So this will give you the final solution. Okay. So this is how the tree of calls of merge takes place when you have an array of 10 elements. So this is just for your reference how it works. Now we will see about the analysis or time complexity of the merge sort algorithm. So we have already seen that general recurrence of any divide and conquer problem is of this structure. So we say that T of n is equal to A or is 1 when n is equal to 1 and A is a constant. Otherwise, in this case, since we are dividing the given input into two halves, okay, so that is the reason value of A is 2 here and value of B is also 2 here. So it was A T of n by B plus f of n. This was the general recurrence. So A denotes number of subproblems. So since it is divided into two halves and we have to sort both the halves, that is why value of A is 2. So if this is 2 here, then n by b denotes the size of each subproblem. So since we are dividing it into exact two halves, so size of first half is also n by 2, size of second half is also n by 2. So that is the reason value of b is 2 here. Okay, and this was f of n. So f of n denotes time required for splitting and conquering or combining the solution. So let us assume that if the list is of size n, okay, then if the value of n, as the value of n increases, more and more time will be required to solve the problem. So we can say that f of n is directly proportional to n. So because f of n is directly proportional to n, we can say that f of n is equal to c of n, where c is a constant. So that is why we are writing this recurrence as t of n is equal to 2t n by 2 plus c of n. So since this is n by 2 here, we assume n to be a power of k. Okay, so n is equal to 2 raised to k here. Okay, now there are many ways to solve any recurrences like this. So for this particular recurrence, to solve or to comment on the time complexity, we will use substitution method. Okay, so what is substitution method is, we are substituting the value of t of n in the same equation again and again until we get a pattern. Okay, so you can see here t of n is equal to 2 we keep as it is, this 2 we are keeping it as it is in bracket, in t of n by 2 it is. So instead of n, we write n by 2, 2t. This itself is we are assuming as t of n. So if this is T of n, instead of this also we have to write 2 T of n by 2 by 2. Okay, so that makes n by 4 plus C of n by 2. Instead of n, we are substituting n by 2, right? So it will be C of n by 2. Okay, plus this C of n remains as it is. This C of n will remain as it is. Okay, so when you solve this, it becomes 4T of n by 4 plus 2Cn. Okay, again, if you resubstitute and solve, it will be 8T of n by 8 plus 3Cn. Again, if you resubstitute, it will be 16T of n by 16 plus 4Cn and so on so forth. Okay, so if you go on substituting, you will see that there is a pattern. Instead of this, we can write 2 raised to k. Okay, now this, when you go on dividing, you will reach a base case where there is only one element in each list. Okay, so this will reduce, your problem will reduce to T of 1. That is the reason here we are writing T of 1. Okay, and when this reaches plus, this will be k into Cn. Okay, whatever is the size of the problem we have seen here, n is equal to 2 raised to k. Okay, so the actual size of our problem, that means k is equal to log n, right? Okay, so k is equal to log n. So if we substitute the value of log n here, it will be Cn into log n, and n is a power of 2. So instead of this, if we write n and T of 1 here, we are assuming as a constant a. So this becomes a into n plus C into n log n. Okay, so you can see here, if this is the equation that we get after solving, then there are two terms in this. One is an, another is C of n into log n. So the dominant term is the second term. Okay, in the second term itself, C is a constant. Okay, so if you just ignore this constant, because it is constant, it will not contribute much to the complexity. So if you ignore C, whatever is the remaining portion is n into log n. So that is the reason we can say, or we can justify, or we can comment that the time complexity of this merge sort algorithm is big O of n into log n. So that is the worst case analysis of your merge sort. Okay. Now the final question that comes is, we have seen that whenever we are analyzing any algorithm, there could be a best case, there could be an average case, there could be a worst case. Okay, so this is, we have talked about the worst case complexity. Now what is actually this best case, worst case and average case with the merge sort algorithm? What happens here is, if you assume the input, that is your shuffled array, if you assume the input to be already in a sorted order, let us assume the given input is already sorted in ascending order. Okay, and to that, if you apply the algorithm of merge sort, whether the way in which the algorithm works will change? No, it will not change. It is again going to divide it into two halves, go on splitting till there is a single element in each list, and then go on applying the combine phase using the merge algorithm. And but nothing will happen in those phases because the list is already sorted. But still, even though the list is sorted, the algorithm will follow the same process and same number of steps. Okay, so this cannot be the best case. Okay, let us assume the list is already sorted in descending order. Okay, so whether that is going to change the way in which the algorithm works, again the answer is no. Okay, so whether the given input is sorted in ascending order or in descending order, or it is randomly shuffled, in all the three cases, the algorithm is going to work in exactly the same way. So that is the reason there is no as such best case or worst case or average case for this particular algorithm, because it is going to function in exactly the same manner irrespective of the type of input you provide to it. Okay, so that is the reason for merge sort algorithm, the time complexity is n log n for best case also, worst case also, and average case also. Okay, So that is all about the algorithm of merge sort, and we have reached the conclusion of this particular e-lecture. So I hope you have completely understood the topic, how to use the algorithm of merge sort, how to solve an example or to sort an example using the algorithm of merge sort, um, what is the sequence in which the recursion takes place, like how the tree of calls is being used using the algorithm of merge sort, how the tree of calls of merge happens. Okay, and I hope you have also understood how we can say that the complexity of merge sort is n log n. Okay, so that is all from my side for this particular e-lecture. For this content of this particular e-lecture, I have used a reference book of Sartaj Sahani, that is a book on computer algorithms. So I hope you have completely understood the topic. If still you have any queries, please feel free to contact me on ngSharma@kkvag.edu.in. So thank you so much. We will stop here. Thank you very much and have a nice day.